Hello, calculus students. Today, Akarsh and I are going to teach you about the first and second derivative tests and what they tell us. So, the first derivative. The first derivative, as many of you guys probably already know, is the derivative of the parent function f of x. And it can be said as f prime of x, function like this. So, f prime of x can tell us many things about its parent function. First of all, if f prime of x is positive, we know that f of x is increasing. And if f prime of x is negative, we know that its parent function f of x is decreasing. Now, if f prime of x is 0, it's a little more complicated than a negative or positive situation. It can be extrema, like max, or min, like pictured here, or it can be neither. And I'm going to explain this more on the next slide. So, this is called the first derivative check. When f prime of x is 0, and it changes from positive sign to a negative sign at the 0, it will have a maximum. Now, if it's vice versa and it changes from negative to positive, f(x) will have a minimum at that point. And there are cases where f prime of x has no sign change, and this is when it's neither, like in the function pictured here, which is very similar to x cubed. It just simply flattens. Well, if this was completely straight and then continuously going up. So it wouldn't change signs, it would just simply have a horizontal tangent here and then go back to positive. All right. So, what is the methodology to find these zeros and find these maximum and minimums? This is what we like to call the number line method. Essentially, you find the signs of the factors of the function to find the overall signs behind or in front of the zeros. So, these points are where we place the zeros. So, the zeros for f of x, and then the factors would go right here. And then, so let's say this is 0 and this is like 2 or something like this. You would take the factors, let's say x plus 3. These these signs most likely won't match these, but let's just simply for an example. So since this is 0, I want to plug in a number behind 0, before 0. So like let's say -1 into each of these functions and figure out the sign for it. And then I'll multiply these signs together. So a negative times a negative goes to a positive. And then you compare these two signs to find if it's maximum or minimum. So in this case, it goes from positive to negative. Again, it's not, this scenario may not be right, but it goes from positive to negative, which would be a maximum. All right, let's do an actual example of correct values. So let's take the function f of x is x cubed minus 3x squared plus 2. So let's take the derivative and find f prime of x. So we know we take the derivative using the power rule and get 3x squared minus 6x. And then we can take this and simplify it into its two factors that are multiplying. 3x times x minus 2. And then again, with these, we can use the number line method. So we know that 3 times 0 would make it a 0, and 2 minus 2 would make the function a whole 0. So these are the zeros of f prime of x. Now, then again, so we plug in -1 because it's right before 0 or any other value before 0 into 3 of x, and we know -1 times 3 is a negative. So this is a negative, and we plug in a -1 into this, and this stays a positive, and a negative times a negative is a positive. And then we can do that again for between 0 and 2, so we plug in 1, so that would be positive. This would be negative, and a negative times a positive is a negative. And remember, like we said before, a positive to a negative is a maximum. And we can do that again here, and we see positive times a positive is a positive, and we know a negative times to a positive is a minimum for the parent function. Let's just double check this. And yes, we're right. And as you can see here with f prime of x, you can see the zeros are here, and it goes from positive, negative, positive. So we determined that x equals 0, the parent function f of x has a maximum and a minimum at x equals 0 and x equals 2. So let's check this. And we're correct. At x equals 0, there's a maximum, and x equals 2, there's a minimum. But there's a lot of questions you'll get in AP Calc which don't necessarily just ask about the function or its local minimum and maximum. It'll ask about the function between boundaries, for example. So let's take this function. F of x is equal to x plus 1 times x minus 2 times x plus 3. From the boundaries x equals -4 to x equals 1. As we can see, there's a clear local max, or in between the boundaries, it would be an absolute max. But there is a minimum here that you would find with the first derivative check, but you wouldn't find simply the absolute max with the first derivative check, as there is a minimum far below down here. So in this case, you would have to find the extrema, the max and min, and then you would also have to calculate for the bounds. So at -4 and -1 to find the true absolute min or absolute max for whatever you're solving for. And this is just the example of the derivative function you would have to plug in with a number line. And then again, absolute max or absolute min with an interval can be found at the bounds as well as the extrema. Now, let's talk about the second derivative. Thank you.
So, now that we've talked about the first derivative, let's see what the second derivative test can actually tell us. So, what is the point of using the second derivative test? Well, it actually helps us understand the shape of a function by helping us determine whether a function is concave up or concave down at a certain point in the function. So, what are the steps to actually doing that? Well, first we have to find the critical points where the function could actually change concavity from their concave up to concave down. Next, we have to find the actual second derivative to apply those critical points to. And third, we have to plug in the critical points into that function, and based on our results from that, we can determine the concavity of our function. So, if we get a positive outcome by plugging in the x value of the critical point into our second derivative, and if that and we get a positive number or a number that is greater than 0, then we get a concave up. Then we know that at that point the function is concave up, so we'll have a U shape, something that looks like that. Or on the other hand, if it's negative, then it'll be concave down, which will be like something like an upside down U shape, right? But what if we get something that's equal to 0? Well, based on that alone, we can't actually make a determination, and we have to look at the points surrounding it. So, for example, let's say that we have a function that we're looking at, our second derivative just kind of touches the x-axis. So at this point, it would be equal to 0, but doesn't actually cross the sign. Everywhere else, it is a negative. It is negative. Then we know that that wouldn't be a point of inflection, because in order for us to have a point of inflection, we need it to cross, thus changing concavity. Because up here, this will be concave up, but down here it'll be concave down. And if it doesn't fully cross that x-axis and change signs, then it doesn't change concavity. And here it is just concave down, even though we have this point that's equal to 0. So let's move on to an example of how we can actually apply this. Let's start off with the function x to the fourth minus 4x squared. And I have this graph of Desmos here for us to see what that looks like. It just looks like that. So our first step, we're going to get to our second derivative by first finding the first one. So here we just did power rule. So we just break down the 4 to get 4x, and then do 4 minus 1 to get 4x cubed. Then minus is our second term. So we do 2 times 4, 8, then our x, and then 2 minus 1 is just 1, which we can just omit the 1. And that's how we get this number. Now we just do that one more time to get the second derivative. So based on that, we do 3 times 4, which is 12x. 3 minus 2 is, or 3 minus 1 is 2. And then our second term is 8x. We just drop the x, and we get 8. So now our critical points are going to be the zeros of our double derivative function. So here it's 12x squared minus 8. So we're just going to plug in 0 on this side of the equation, and I used a graphing calculator for this. So once we get to that, this is what our first derivative looks like, if you want to see, and this will be what our second derivative looks like. And in this case, you can either plug it into the algebra or just use the graphing calculator, and you can see that these are our points. So now that we have that, we need to actually figure out whether the function is actually positive and negative, and that'll tell us the concavity. So going back to our function here, we can see that in between these points, in between negative 0.817 and positive 0.817, the function is completely negative in between those two. So on our number line, that's represented by this negative sign. And elsewhere, if the function is less than negative 0.817, or if the function is greater than 0.817, then we can see that the function is actually positive. And that results in this would be concave up here, or this was referring to f of x. F of x would be concave up when it's less than 0.817 or greater than positive 0.817, and concave down when it's in between the two. And that is how we can use the second derivative to identify what parts of the function are concave up and concave down. We know that during these points here that we can't fully determine whether the function is concave up or concave down. We have to look at the parts surrounding it. So if you don't have access to a calculator, what you do is you would just plug in, say, like negative 10 and see, do you get a positive number or a negative number? And in our case, we can see that, just look at the number line, that we should get a positive number. And then you just want to keep plugging in points that are in between the two segments. So maybe a point that's here and a point that would be somewhere over here. So for this, we could just plug in f double prime of 0 if you want to find whether it's concave up or down in between the two critical points. And if we're looking for greater, we can plug in something like positive 10 or even positive 1, something like that. Because going back to our previous slide, we know that our function is 12x squared minus 8. So if we plugged in like something like negative 10, we know that we would get a positive number, because let's say negative 10 squared would just be 100, positive 100. And we know 100 times 12 minus 8 is definitely going to be a positive number. If we plug in 0, then we just get 0 on that side on this side of the equation, and we're left with a negative number. If we plug in a positive number again, it would be the same situation as what we did for negative 10. And that will be how we determine the concavity of our function.